Okay, let's start. So it's a pleasure to have Prashanth here giving 2 lectures. So the topic of the first lecture is complete monotonicity and the dual volumes based on the work with Johannes and Elia. Please, Prashanth.
Yeah, thank you. I would like to thank the organizers for putting together this wonderful workshop and giving me an opportunity. So I'm going to talk about some recent work with Johannes and some work in progress with Elia, who's a PhD student in Munich. So the broad context is, so we have learned over the last week and this week as well, that broadly integrands have very nice properties. And so these are nice rational functions. In certain cases, they are volumes of some geometric objects and so on. So the broad context is we want to understand if some of these nice properties are inherited by the integrated objects. Inherit. Okay. And the way we go about addressing this very broad question is that we are very fortunate to have a wealth of perturbative data currently, especially in the context of n equals 4 superangles. So the 6-particle amplitude, for instance, the 6-particle amplitude MHV has been computed to 8 loops. So we have all this perturbative data lying around. And the thing we did is we looked at some of this available data, and then we tried to see if these transcendental functions, so the integrated objects have some transcendental functions. They have some nice properties. Okay. So that's the question we asked. And it turns out they do in certain cases. Very broadly, being very schematic here, this object has some expansion, let's say with respect to coupling. And what we find very, very schematically is this object has infinitely many positivity properties. Okay. And so the question we can ask now, that because this seems to be some generic property that seems to transcend different loop orders, the question you can ask is, does this hint at some deeper structure? So what I'm going to do is basically I'm going to tell you what these infinitely many positivity properties are. I'm going to relate it to some notion in mathematics which is quite well known. And then later we are going to see that this notion has a geometric connection. Okay. So the plan today is very simple. So I'm going to tell you what these positivity properties are. And I'm going to give you examples of quantities we care about which satisfy those properties and why. Okay. So any questions before I get started? Cool. Okay, so let's start with basically some definitions, because I have to tell you what these properties are. giving you a mathematical definition for a smooth function, say in one variable. This function is called completely monotonic. In some region R, let's say subset of the real line. If it satisfies the following property. Okay. So there's infinitely many conditions. So I'm basically saying, so this is true for and for every point in the region. Okay. So there's infinitely many conditions which holds for every n from 0, 1, 2 all the way, and for every point in the region. Okay. So in particular, I mean, if you restrict to n equals 0, this tells me that f of x is positive. If I restrict to n equals 1, it's telling me that the first derivative is negative, which means it's a decreasing function. And if I restrict to n equals 2, telling me that the second derivative is positive, which means that this function is convex. Okay. And then we have infinitely many others. Okay, so if we plot these functions, this is the thing you can do. If you just plot the function, since it's supposed to be monotonically decreasing everywhere, it's going to just have a boring graph like that. Now if I plot, I don't know, let's say the 50th derivative of the function, that's also going to look like, it's also going to have the same shape. Okay, so if this function has a Taylor expansion, let's say around some point x naught, then basically the property is telling me that all of these Taylor coefficients, they alternate in sign. Okay. The property is slightly more general because we are going to look at functions which have logs and so on. So it may not have a Taylor expansion on certain points. But as a condition on the derivatives, the property holds. We'll check. Okay, so let's look at some examples. So the way I've defined the property, so there are two crucial inputs. One is basically the variable, because I'm taking derivatives. And the second thing is basically the region, because the property has to hold at every point in the region. So these are both crucial inputs. So if I have to tell you the property, I have to specify what variable in what region. Okay. So let's look at this function. And this function is Cm. So I forgot to tell you, we will abbreviate completely monotonic as Cm. Okay, here on. So this function is completely monotonic. Okay. So is it clear why? I mean, proof is actually quite straightforward. Just compute the nth derivative. And you'd see that this quantity is just it is manifestly positive. Okay. Second simple example with this function. Which is also CM in the same region. Okay. Again, proof is very straightforward. Okay, so sort of third, slightly different example with this function minus log x. This is CM. Should write lower. Apologies. Okay. So again, quite simple. I mean, proof can be one line. I'll not write it. Now we can look at an example, which is we can look at a non-example. So we can look at this function, 1 by 1 minus x. And this is not CM. On unit interval. Okay, and it's clear why this is true. So this function blows up at x equals 1. So it has a graph that looks like more like that. So it's an increasing function. And from whatever I told you, they have to be decreasing functions. So it cannot be CM. Okay, and a final example. This function and this function cannot be CM on any interval which contains 0. Okay. The logic here is that, so as I go close to 0, the log basically takes arbitrarily large negative values. Whatever this constant a is, this function is going to change sign. So cannot be CM. Okay. Now, I mean, next I'm going to talk about a few properties, but is the definition and the examples clear? Okay. Now I'm going to talk about some basic properties. This class of functions has several nice properties, but we're only going to look at one or two which we are going to actually use. So the first property is if I have two functions, call them f1 and f2. These are CM in some region R. look at some convex linear combination of these functions. And this is also CM in R. Okay. So what this property means is that the space of CM functions is what is called a convex cone. Okay. So usually we are used to a vector space where you take elements, you take scalar multiples of those elements, you add them up. But here, all constants are not allowed. We are only allowing positive constants. So that's what makes it a cone, not a vector space. Okay, so second property is that this is a class of functions that's closed under products. Okay, so by that I mean okay. The proof is again quite simple. It's just a product rule for derivatives. So this is true because both of these terms are by themselves positive because it's CM, which means the whole thing is also positive. Okay, so this was all in one variable. There's a generalization to several variables. Yeah, actually I don't need to erase this. I can just modify here. I have a function of n variables. And this is completely monotone. Some subregion of Rn. Okay, so it's a completely straightforward generalization of whatever we saw for one variable. And all the properties I discussed for one variable also carry forward to the multivariable case. Okay, so just to give you an example, I can look at this function. Okay, so it's a linear function in all my variables raised to some power. So if the coefficients and basically the power I'm raising it to are both positive, then this function is completely monotonic. On the positive orthant. Okay, so now I've defined what this property is. Now we can come back to physics and I can tell you what are the physical quantities for which we observe this property. So the first quantity is cusp anomalous dimension. Which you heard about in Johannes' talk last week. We have a Wilson line which has a cusp, and then as Johannes argued last time, so the expectation value of this Wilson line has a UV divergence. Which I'm going to denote as cusp phi, where phi is this cusp angle. And basically the statement here is if I choose x to be this particular phase of my cusp angle, and let's say this cusp angle has a perturbative expansion. I'm very schematically denoting like this. Okay. Then the statement is so this is the claim. Okay. So yeah, I should have said, sorry, this is looking at gamma cusp in planar n equals 4. So this has been computed till 4 loops. We have data available for this. And what we try to do is basically look at this available data, and then initially we are able to sort of run various numerical checks to see that this property holds. And then we can also analytically prove it, because the functions that appear are simple enough, at least the first few ones, okay, by the properties I told you, things like so just to give you a sort of a trivial example. So at one loop, this function just looks like this. Okay. And from the examples we looked at, we know that minus log x, 1 by 1 plus x, I mean, 1 minus x was not an example, but it's actually easy to see, right? It's positive if x is between 0 and 1, and first derivative is minus 1. So minus for the first derivative is positive. So this is also CM. And then from the property I argued about products of CM functions being CM, you can see that this function is CM.
Can you explain here? So the physical value for gamma cusp is x is 1, the standard value of the undeformed in this notation.
Can you repeat the physical value of?
Well, like the normal gamma cusp, not the deformed one.
Yeah, so the normal gamma cusp, yeah, okay.
So this is kind of a 3-level gamma cusp in a sense, because it evaluates to 0 for x is 1.
So this gamma cusp, when I take phi to infinity, yeah, so if I take dealing with this. Okay, in phi, okay, so let me state this in phi. I want to make a mistake translating it to x. If I'm taking phi to infinity, then this morally goes like gamma infinity times some log, or times phi here. Okay, and this gamma infinity cusp is the one which just depends on the coupling and which is known by integrability to known exactly by integrability.
Hello.
Yeah.
Is the statement that the integrand of gamma cusp, that is also CM?
We are only talking about integrated quantities.
Okay, but you started with integrand being having some property, and then you.
Yeah, so that was the motivation, broad motivation. We wanted to understand the properties of integrated objects.
Okay.
Okay, to see if some nice properties of integrands survives integration.
Okay.
Okay, that was just the broad motivation, and the way we went about doing it is we used the available data. So we sort of looked at these functions, tried to see if there's something nice about them, and this is one observation. I mean, like we see that these functions have these properties.
Okay. Okay.
In some cases, we can numerically show it. I mean, numerical evidence. In other cases, we can actually prove it by some elementary arguments, this kind. Okay, so that's the. Okay, so second example is.
Sorry, can you clarify? Do you verify that gamma cusp is CM, or do you prove that it's CM?
So in this particular case, we can prove it. Okay, by using a combination of these sort of elementary arguments. Okay, and some other things I'll tell you. Curiously, what happens is gamma cusp is also known in other theories. It's also known in QCD till 3 loops and QED till 4 loops. There also we see the same property. Okay, there we only have numerical evidence. There we don't have a proof. Any other questions? Okay. So the second sort of quantity we looked at, 4-point. Okay, so this is a 4-point amplitude. So in general, it would depend on 3 parameters. So I'm looking at a very special Coulomb branch, I mean where I have only one mass. Okay, so it would depend in general on 3 parameters. But since n equals 4 has dual conformal invariance, it turns out things actually depend on just 2 variables instead of 3. We call them u and v. And for this particular object, the statement is okay. So this is a statement. I'll also probably tell you how we can show this in this particular case. Okay. So before telling you how we know this, I'll have to introduce another property about CM functions. These amplitudes are not infrared divergent. I think the mass rate. Sorry?
Coulomb branch, you will have charged particles also, right?
Yeah, so I think external particles are not charged.
So you are considering neutral particles.
Yeah.
I see. Okay. I'm a little confused because you also introduced mass, right?
Yes, the internal, basically the...
Oh, so this is the mass in the internal.
Mass in the
So external particles are just photon-like objects. Okay.
Okay, so the way I introduced the property, it was some very simple thing about derivatives that you can check. But there are infinitely many conditions. So in practice, if I give you a function, this is not an easy thing to do. There's no way for you to, if I give you some arbitrary function and show that it's CM. But it turns out, if your region is just a positive orthant, then there is a complete characterization of these functions. Okay. So this is a theorem by okay, and basically the statement is the following. So if I have a function of n variables, and this is CM in the positive orthant, if and only if it's a multivariate Laplace transform of a function mu, which is positive. Okay, so this is a characterization of these functions. So in principle, if I give you any function of n variables, which is CM in the positive orthant, you can do this inverse Laplace transform, and you can show that this measure is positive. Then that proves it's CM. You don't have to do any work. But in practice, this is a very hard thing to do because inverse Laplace transforms are not easy to compute for generic functions. Okay, now going back to Coulomb branch amplitudes. In a paper in 2013, Simon Karenhuo and Johannes Henn they computed these amplitudes up to 3 loops, and they also showed the following nice thing, so that these amplitudes satisfy a Mandelstam representation. Okay, so they satisfy this sort of a representation where this delta is basically this region. Okay, so I'm integrating d xi d eta over this region. Okay, and we have this representation of the amplitude in 3 loops. Yeah, so that representation is actually the basis for us to prove this fact. So the way it works is, write it again. Okay, so the first thing I do is these factors, the 1 by xi plus u and the eta plus v. I apply our favorite Schwinger trick. And write this as okay. And I do this for both of them. I do this for 1 over xi plus u, and I do this for 1 over eta plus v. Let me call this yi, just for simplicity. Okay. So if I do this for both of them, then I can rewrite my integral. That. And now you see where I'm going with this. So I want to sort of use that theorem to argue this fact. Okay. So then basically I also have to interchange the integrals now. This is the step which would be questionable mathematically, but you can do this interchange and you can numerically compare whether it works. Okay, this is the simpler ones. Okay, and I get this representation. So by the theorem, now this is what I would interpret as my mu of, sorry, this should be y1 and y2. Yeah, so by the theorem, this is what I would interpret as my measure mu. If this is positive, then the property just follows. Okay. So the theorem says it has to be a Laplace transform of something positive. We have written it in that form. So it's going to be Cm if this measure mu is positive. So it turns out that L equal to 1 and 2, this rho is actually positive. Okay. So if rho is positive, then there's nothing to do, right? Because we are integrating positive functions over a positive region, right? So then nothing can go wrong. But at 3 loops, this function actually changes sign, so it's not always positive. But this integral still is positive. Okay, so somehow the property is saved, even if my kernel or whatever I started with is not positive. Any questions? I'll stop and too fast. Yeah. So the property only cares about mu, right? So rho can be negative as long as this whole integral, because I'm multiplying it with some exponential factor and then integrating, right? So if the whole thing still remains positive, then we don't have to do anything. That's the idea.
Hello. Yeah. So how do you see that when rho is negative, this whole thing is still positive?
I mean, in this particular case, we can see it explicitly. I mean, that is the. In general, it might be a hard thing to do. I agree, but in this particular case, we can actually see it. Okay. So this rho has many terms, but you can divide it into a bunch of terms, and then separately you can see it, and then you can argue the whole thing is positive.
So, for example, in the L equals 2 result, or even L equals 3, if you write the result as a sum of terms, I guess each individual term does not have the property. But are there any sectors, kind of, can you regroup the terms into groups which already are Cm by themselves? Or is it only the property of the full amplitude, not?
Yeah, we did not really examine all the individual pieces in that way. As I stated it, it's only thing for the full amplitude. Yeah, but that's definitely an interesting question. I mean, maybe something to study. We have not thought about it.
Suppose that you do just a single diagram, let's say, do some of the diagrams already have the property? Okay.
Yeah, so I'm going to come to that next. So scalar integrals, so in general, I mean, away from the story, scalar integrals which have a Euclidean region, we can argue are Cm. Okay, I'm going to give you a proof in next in 5 minutes. But if you have numerators, okay, basically the proof goes via Feynman representation. Okay, if you have numerators, then because you would divide it into some combination of scalar integrals which can have relative negative signs, the property in general can be ruined. Okay, individually each piece has the property, but relative signs can ruin the property. But in some theories, nice theories like n equals 4, it turns out that even with numerators, there are examples of amplitudes which are Cm. Okay, one example, okay, I'll just mention it because you asked the question. So the chiral pentagon that you talked about in your lecture, right? And this is this particular combination of okay, so it's that function, okay, and this function is Cm. Okay, so let me tell you why it's Cm. So what I'm going to do is I'm going to call this function FUV, and I'm going to look at that guy. And now, so one nice thing about this function is that if I sort of take a double discontinuity, so I take a discontinuity in U and then a discontinuity in V, only the log term contributes. Okay, so it is a trivial sort of double discontinuity. Okay, so it's very much in the spirit of this particular representation. So we have this rho, which is, so let me just write down the answer. Okay, so it just looks like that, where this rho is actually just this rational function, 1 by y1 plus y2. And by the same argument, this combination is Cm. So this function is Cm. Okay, but this is not the function I started out with, right? I'm just looking at this f. So what I do is I multiply both sides. By 1 minus u minus v. So 1 minus u minus v, that integral. Yeah, so I multiply 1 minus u minus v by that integral. Now the point is, just like the 1 minus x in the gamma cusp example, this guy is Cm, but it's Cm on a smaller region. Okay, and the whole integral is Cm whenever u plus v is positive, u and v are positive. Okay, so it's also Cm. In that region. So the chiral pentagon is basically Cm in that particular region.
But in this case, it's basically a canonical form on a triangle.
Yes, so that's another nice connection. So this is all related to what are called Eomoto polylogarithms, and I'm going to talk about that next time. I mean, there is a connection between this property and these objects. Yeah. Any other questions?
Just one question. So why are we targeting to prove if something is CM or not?
So the way we started out with data, right? We just had functions. Then we saw something curious by doing numerics, right? How do you know it's real? Like, I mean, you could go, right? I mean, so that's why we're trying to prove it. And then the point is that, what does this teach us, right? I mean, the function having this property and so on. So as we'll see, I mean, the way I've introduced these functions, it seems like there is absolutely nothing geometric about them, right? We're taking derivatives of some crazy function and checking signs, right? But it turns out these things actually have a geometric connection, okay? So to I mean, sort of jump ahead, basically this theorem that I told you about for the positive orthant, so we have an analog of that theorem in a projective space, which expresses these functions as some sort of integrals over the dual of the region where it's Cm, okay? And the 0 infinity happens to be self-dual. Okay? That's why it's large transform here. But in general, you're going to have something more complicated. You're going to have integral over some interesting region with a positive measure, which you can think of as volumes in some context. So somehow it's also going towards that, okay? Yeah, we don't understand everything. I mean, we don't understand most things very well. Still very exploratory, but it seems like there are some connections and we're just trying to explore. Okay. Okay, and so next I'm going to sort of go away from n equals 4. I'm going to talk about scalar Feynman integrals. So let's say I have some Feynman graph. Loops. We are in 4 minus 2 epsilon dimensions. Okay, it's sort of very convenient representation of this object is via its Feynman parameterization. So I mean, just to connect, let's say I morally looks like okay. So this morally looks like that. The product of 1 by product of propagators raised to some powers nu I. Then what you can do is you can sort of recast this in the following form. It looks a bit complicated here. This U and F are graph polynomials. But the nice thing about this particular representation is that I don't need any other information. I can just look at the graph, and these U and F are basically things I can write down. I can derive directly from the graph. Okay, so given a graph, I can just look at the graph. These are some sort of counting things associated with the graph. You could think about it like that, some combinatorial thing, and you could just write it down from there. U alpha, I'm just defining them. For okay, and so I'll also tell you what these symbols mean. Okay, so T1 here is a spanning tree. T2 here is what is called a two spanning forest. Okay, so to give you an example, let's take the simplest one. Let's take the bubble. What I would do is I would associate an alpha to each internal propagator. And the spanning tree is basically something which is connected and which covers all the vertices of the graph. Okay. So in this case, there are 4 vertices. So the 2 sort of allowed spanning trees are okay, only those. If I delete any other edges, then it's no longer connected or it does not cover all the vertices. Okay, that's the idea. So this is sort of T1. And this formula here tells me that I need to take products over those alpha i's which are not in the spanning tree and then sum over them. So this would tell me, for example, 2 alpha is alpha 1 plus alpha 2. Okay. So that's what this formula is telling you. So 2 spanning forest is something very similar. The only difference is that it's not connected, but it's 2 connected. So you basically divide your graph into 2 connected components. Okay. The union of these covers all the vertices, but that's just the idea. So for this case, there is only one such guy, which is okay. And this particular term here is basically telling you I have to look at those edges which are not in my 2 forest and then multiply it with this particular guy. So the F here and this particular symbol STR means basically I'm summing over squares of the momenta of things which don't appear in my 2 forest. Okay, so there's only one such thing here. S would be Mandelstam S. It would be, you can check sum of these 2 momenta squared, which I call S. Okay, just to complete slide. Okay, so that is the Feynman parameterization. And so 2 things to remember here. One is that basically my U polynomial, whatever I call U alpha, is independent of kinematics. Okay, it just depends on these alphas which we integrate over. Doesn't depend on anything else. F has dependence on kinematics. But only linearly. Okay, so there's nothing quadratic. I mean, there's no S squared, there's no m to the 4 in the okay. That is sort of the crucial input. So now, I mean, in the slide, in the thing that I just erased, I told you that this particular function is Cm if the C's and the alphas are positive, right? And you can see that our integrand is exactly that object. Okay, we have this s and m squared, but they are multiplied by something positive. Okay, so what this is telling us is that okay, this is what it's telling us. So if we can choose basically minus str to be positive, then this function is CM. Okay. Some comments basically. So the way I've done it, I mean, the proof works only if the integral is actually convergent. Okay. So that's the. If I is not convergent, and let's say I has some Laurent expansion in my epsilon, then you can actually argue that the leading coefficient still has the property, okay? But the subleading ones in general don't have the property. So the property is lost. And there are also these interesting dimension shift operators, dimension shift identities that Ekta talked about. So you can use those to sort of say something interesting about the lower coefficients, if you like. But in general, I mean, they're not CM. It's the first remark. Second remark is that I told you it's CM if we can choose this, right? So this choice may not be possible in certain cases. Okay. So in the way I wrote it, it seems like these SS are all completely independent, but they are not. They satisfy various relations, as we know. Okay. So in some cases, basically, this choice of a region where we can choose all of them to be positive might itself not exist. Okay. Just to say a bit more about that. So the region where the f polynomial is positive, it's completely positive, is called the Euclidean region. This exists if you have planar integrals with no numerators and so on. But if you have non-planar integrals, I mean, the region may not exist, especially if you have massless particles. So one example is okay. So, and let's say the external particles are massless. So we have this relation. And if I use it in my f polynomial, okay, so basically I end up with some terms that look like this. Okay, and basically since you are integrating over alpha from 0 to infinity, you see that, I mean, this function in general is not always positive. So Euclidean, there is no such region where f is positive for all phi greater than 0. Okay, so in cases like this, basically it does not hold. There's no region for it to be CM. Okay, so one last comment and then we can move on. So let's say I do this, okay? Let's say I do this for the 6T box. Okay, epsilon is minus 1. And then basically the answer I end up with is this function. Okay. So this function is CM. You can check all of the properties I told you. It works out nicely. But notice that it comes with this particular factor, 1 over s plus t. Okay. So generally in practice, when people do computations for various regions, they choose to normalize the amplitude in different ways. If I normalize this amplitude in such a way that I strip off s plus t, then I will not see the property. Okay. So that function basically has a minimum whenever t equals s. So it cannot be always increasing and decreasing, and so it doesn't work. Okay. So normalization factors are crucial. That is the
Can I ask here? So if the normalization is important and you don't always choose the one with unit leading singularities,
yeah.
is there a logic at the level of integrand which normalization you choose? Because you get non-unit singularities then on the integrand level, but it makes the integrated CM. So what's the...
So, so I don't know, like it seems like at the level of the integrand, it's very clear when it has the property and when it doesn't, right? But after you do the integral, you can end up with things like this or even more complicated. Then, I mean, if you normalize with if you normalize in any other, I mean, if you don't normalize in such a way that it doesn't respect this thing, then property seems to be lost. So in general, I don't have a rule to tell you, but I mean, one small comment about this function. So I told you that it's CM, right? I mean, it's CM whenever S and T are negative, right? So notice that if I put S equals minus T, then you would think that this function is singular because I have a denominator which is S plus T. But it turns out the numerator, because it gives me some I mean like log of minus 1 squared, and numerator also vanishes at the same point. Okay, so somehow the whole thing is, there's nothing funny which happens at t at the point t equals minus s, even though it seems like that, the level of the, and that is important because when you say this, this property holds in this region. Okay, so I did not get into this, but generally the property holding in a particular region also means that the function is analytic in that region. There is an analytic extension of these functions, even though I'm only looking at real variables here, okay, of the function. So it has to be sort of not badly behaved in the region, otherwise it cannot hold. Okay, so one sort of quick way to see that would be from the Laplace representation. So I gave you a precise statement to tell you when this would be CM. This would be CM if this is some so this guy would be some right with mu positive. Now a Laplace representation, sort of a Laplace representation in general converges in a strip. It doesn't converge in, so this guy generally would converge for real part of S, real part of T, bigger than some value, beta. Okay. So what that allows me to do is it allows me to now extend basically this function to complex variables, where I add an imaginary part to my t and s. So in some Euclidean sort of tube around my Euclidean region, basically I get an analytic extension. Okay. So the function basically cannot have singularities, and this sort of leading, I mean, unless I divide by that factor. Yeah, so the normalization in this case basically respects that. That's the only thing I wanted to say. Okay. Okay, so in the last 10 minutes, I will tell you about one last object in n equals 4 we looked at. Okay, it's a real mouthful, but I'll explain what these words are. So we are looking at 6 gluon scattering in n equals 4 superangles. Okay, and generically, if I have some, I call A and K to be n particle amplitude where the K particles have one helicity plus, let's say, and the other K plus 2 particles have one helicity, let's say plus, and the others have minus. In general, I mean, this as an n particle amplitude, this is going to depend on, as we know, Mandelstam invariance. And in general, there are going to be n into n minus 3 by 2 of them if I'm in large enough dimension, or there will be 3n minus 10 of them if the number of particles is more than the dimension. But in this theory, because there's dual conformal invariance, it turns out I don't directly work with Sijs, right? I would have to look at, just to be a bit more clear. So we go to planar variables, so each momenta can be written as so general Mandelstam is related to Xijs like that. But due to dual conformal invariance, I don't work with these Sijs directly, I only look at some cross ratios in the Xijs. So this number, 3n minus 10, actually reduces to 3n minus 15. Okay. And so the answer only depends on some cross ratios. Okay, so we are looking at 6 particles, so the answer is basically a function of 3 variables. We call them U, V, W. And as you heard from Johannes' talk, and also Yara reviewed it in his last lecture, but this object generically has higher divergences. Okay, but the IR divergence sort of factors out as a universal This is the BDS story that you heard. Okay, so this ANIR is basically what was referred to as BDS. Morally, it looked like some exponential of gamma cusp infinity times the one loop amplitude. Okay. And this particular BDS ansatz was nice because it respected dual conformal invariance and it was sort of smooth under collinear limits. But there's sort of another, so there's no unique way to do this, right? I mean, because the IA and IR is some divergent quantity, so I can always add something finite to it, right? And it would still be a good regulator if it respects some properties. So there's an alternative thing in the literature, which is called BDS-like, which is sort of related to BDS in the following way. This function sorry, 60 for 6. Okay. The exact details don't really matter here. I'm just saying this to sort of precisely state for what function the property holds and so on. So we normalize by BDS-like. And usually it's also customary to divide by the tree level amplitude. Okay. And this object is basically the BDS-like normalized MHV6 particle amplitude. And that's the object for which I'm going to state the property. Let's say this guy again has some expansion, coupling expansion. Okay. And then there was a positivity conjecture about this object. Okay. So in 2014, Arkani-Hamed, Andrew Hodges, and Jaroslav Trnka we noticed that the integrands that I have in this case, which can be thought of as canonical form, comes from the Amplituhedron. When I look at kinematics, external kinematics which lie inside the Amplituhedron, that object was positive. Okay. Based on that, they basically made a conjecture about the existence of a dual Amplituhedron, okay, which would explain that positivity property. Then further in 2016, you not write the full, yeah. So Lance Dixon, Matt Hippel, Andrew McLeod, and Jaroslav Trnka yeah, it's fine. Yeah, so they basically further checked this particular property. So in this 14 paper, they basically conjectured very generally that many objects, like the log of the amplitude and this ratio function and the reminder function, and these objects should have some positivity properties. Okay, so in 2016, in basically this paper, they did explicit checks of, in particular, this object. Okay, so this positivity conjecture, just to state it, is that basically you're looking at this region. Okay, so this is actually the 6-particle. This is when the kinematics lies inside the 6-particle tree Amplituhedron. Okay, these are the conditions on UVW. And the conjecture basically was that okay, so that was the conjecture. So I should also mention that this object has been computed to, this is one of the data I was talking about, it's been computed to very high loop order. It has been bootstrapped to very high loop order. So we have analytic results. Okay. And so basically the development from our side is that we study these objects, and for L equal to 1 and 2, and there is also a sort of strong coupling result that is available from ADS-CFT on the special slice where U is U equal to V equal to W. Okay. So these guys we can prove. And for 3 and 4 loops, we have numerical evidence. Yeah, so our conjecture is that this object is not just positive, it's actually CM in this region. Yeah, I'll stop here.
Thanks a lot, Prashanth. Questions? I already had many questions during the lecture. Are there any more? Shruti.
Sorry, maybe you said and I missed it. Are there examples that you have worked out that are not CM?
Yeah, there are many examples. I mean, like very trivially, I mean, one example would be like, I talked about scalar integrals. You can look at things like box minus triangle. These sort of things in generally are not CM. So it is a very special property. It's not, I mean, it might seem like from the way I presented everything is CM, but it's not the case. I only presented cases where it actually works. There are many examples where it doesn't work.
I have also a question. So is it possible to check something just at the level of symbol? Even like, for example, I give you a symbol and you said there is no way how this is CM. So whatever you add beyond the symbol, you cannot do it. Or other way around, it's potentially could be completed, despite you cannot say for certain, but.
Yeah, it's a bit tricky, but I mean, like we did look at some things. So one nice thing about the property is that certain iterated integrals, you can see that the property just recurses. Okay, so without any work, you can just say, one classic example would be this function. So let's say I start with some f0 of x, which is 1 by 1 plus x. Okay, and then I define iteratively t okay, or even doesn't matter, something like this, some iterated integral of this kind. Then you can see that this whole family is basically CM. Everything goes through naturally, because if I write down F1, zero to infinity. Let me put 0 to infinity. Okay, and the x dependence is very simple. It's only enters through this linear factor. So I can just differentiate under integral sign, and I can see that CM. And this holds at for any n. Right? The n minus 1th object, even though it can be complicated, only enters only as a function of the integration variable. So in x, basically, I can trivially see it's CM. Okay, so there are many such examples, but we don't have any general thing to say. I mean, like, cannot make a claim about at the symbol level. We don't yet have a statement.
Okay, thank you. So if there are no more questions, thanks a lot, Prashanth, and let's go for lunch.